Hello everyone. So welcome back. Our today's topic is representation of graph using adjacency matrix. In the previous lectures, we have seen what all the terminologies are there related to graph and the directed graph. So let us move on towards adjacency matrix. So there are three common ways of storing graphs in computer's memory. Okay. So the first one is sequential representation by using an adjacency matrix. The second one is linked representation by using an adjacency list that stores the neighbors of the node using a linked list. So this second approach we are going to see in our next lecture. And third is adjacency multi-list, which is an extension of linked representation. So let us see what is adjacency matrix representation. An adjacency matrix is used to represent which nodes are adjacent to one another. Means what are the nodes that are neighbor to one another. By definition, two nodes are said to be adjacent if there is an edge connecting them. So in a directed graph G, if node V is adjacent to node U, then there is definitely an edge from U to V. Means both the nodes are connected with the help of an edge. That is, if V is adjacent to U, we can get from U to V by traversing one edge. For any graph G having n nodes, the adjacency matrix will have the dimension of n by n, means n rows and n columns. Okay. So in an adjacency matrix, the rows and columns are labeled by graph vertices. An entry Aij in the adjacency matrix will contain 1 if vertices Vi and Vj are adjacent to each other. Means what? There exists an edge between Vi and Vj, then the corresponding matrix entry Aij will contain 1. Otherwise, it will be set to 0. So, in short, if Aij means if there exists a edge between Vi to Vj, then the vertex Vi and Vj are said to be adjacent to each other. So, the corresponding adjacency matrix entry will have 1 in it. Otherwise, it will have 0 in it. Since an adjacency matrix contains only zeros and ones, it is called a bit matrix or a Boolean matrix. The entries in the matrix depend on the ordering of the node in G. Therefore, a change in the order of the node will result in a different adjacency matrix. So, the next figure shows some graphs and their corresponding adjacency matrix. So here are 4 examples wherein which we have represented graph using adjacency matrix. So let us move on to this first example of directed graph. So if you can see that there are total how many vertices? A, B, C, D and E. Means there are 5 rows and 5 columns in the adjacency matrix. So if you can see, here exists an edge between A to B. Okay, so edge is there from A to B. So we have written 1 in this row and this column of 8th row and Bth column. Okay. Now if you can see, there is a no edge that is connecting from B to A. So this Bth row and 8th column will have 0 entry. Now if you can see, there is a row, there is an edge exists between A to D. So it will have corresponding entry as 1 in adjacency matrix. Similarly, there is an edge from D to E. So it will have corresponding 1 entry in the adjacency matrix. Similarly, you have an edge from E to C. Then it will have the corresponding entry as 1 in the matrix. Similarly, you have C to B, then it will have the corresponding entry in the Cth row and B column in the adjacency matrix. If you see an directed graph with loop, means there exists a loop from B to B. So if there exists a loop from B to B or any vertex to any vertex, then corresponding entry will have 1. Like bth column and bth row will have 1 in it. Okay. Now here you can see there is an edge existing from C to D. So C to D will have 1 in the adjacency matrix, and there exists an edge between D to C, means starting from D and ending at C. So again you have Dth row and Cth column as 1. Okay. Now let us move on to a third example, that is undirected graph. Here you don't have any direction. So means what? You can traverse in both the direction. Means what? If you are having an edge between A and B, then you can traverse from A to B and B to A. So Ath row and Bth column will have 1. Similarly, Bth row and Ath column will have 1. Now there exists an edge between E to D, then you can traverse in both the way from D to E and E to D. Hence the Dth column and Eth row will have 1 and Dth row and Eth column will have 1. Likewise for the other edges. Now you are having the fourth example as weighted graph. So here you can see that instead of putting ones for representing edges in the adjacency matrix, we have put the weight given on the edge. So there exists an edge from A to B which is having a weight of 4. So Ath row and Bth column will have value 4 instead of 1. Similarly, if you can see, there exists an edge between B to D, so which carries weight of 7. So Bth row and Dth column will have value 7. Okay. So instead of putting ones against the edge, we are putting the weight that has been given to the edge in a weighted graph. I hope you have understood. So from the previous examples, we can draw the following conclusion. That is, for a simple graph that has no loop, the first one, the adjacency matrix has zeros on the diagonal. So that has no loop has an adjacency matrix with zeros on the diagonal. The adjacency matrix of an undirected graph is symmetry. Symmetric means what? It will be symmetric on the both the side of the diagonal, if you can see the values. Okay, the memory use of an adjacency matrix is order of n square. Why? Because if there are n edges, then we are using n rows and n columns, that is n by n matrix. So that becomes order of n square. So number of ones or non-zero entries in an adjacency matrix is equal to the number of edges in a graph. The adjacency matrix for a weighted graph contains the weights of the edges connecting the nodes. Okay. Now let's move on. The powers of an adjacency matrix or path matrix. So in our previous example, we have seen that if there exists a single edge between the two nodes, we are writing it as 1. Okay. But there may be a case that there is no direct path, but there is an indirect path between the nodes. Means there is a, let's say you are having a node Vi and you are having a node Vk. So there is no direct edge from Vi to Vk, but there could be an edge from Vi to Vj and then Vj to Vk. Means what? There comes two edges in between the path to reach from Vi to Vk. So that becomes the second power of the path matrix. So in the previous example, we have seen matrix A raised to the power 1. We can conclude that an entry 1 in the ith row and the jth column means that there exists a path of length 1 from Vi to Vj. Now consider A square, A cube and A raised to 4. So a of ij square is sum of a of ik into a of kj. Okay. So an entry a of ij is 1 if a of ik is equals to a of kj is equals to 1. That is, if there is an edge vi to vk and vk to vj, then there exists a path from vi to vj of length 2. Okay. If you see it with the help of example, there exists a node vi. Okay. Then there is exists a node vk. Okay. You are not having any direct edge between vi to vk, but you have an intermediate node vj. So you are having one edge from vi to vj and vj to vk. In this way, these are directly indirectly connected. Okay. Means what? There exists a path from vi to vk, but with two edges in between. So the length of the path is 2 here. Okay. Had it been a direct edge from vi to vk, then the length of the path would have been 1 here. I hope you have understood. Now let's move further. Similarly, every entry in the ith row and jth column of A cube gives the number of path of length 3 from node Vi to Vj. In general terms, we can conclude that every entry in the ith row and jth column of A raised to n, where n is the number of nodes in the graph, gives the number of paths of length n from node Vi to Vj. Now, if you consider the directed graph given in the next figure, given in the previous figure, we can have an adjacency matrix A. Let us calculate A square, A cube and A raised to 4. So, here is a directed graph with its adjacency matrix. Now, you know that how to calculate and how to create an adjacency matrix from a directed graph. So, you are having this adjacency matrix already. This is A raised to 1, or you can simply call it as A. Because if there is a single edge between any two nodes, it is writing it as 1 in the corresponding adjacency matrix. Now, if you want to calculate A square, A cube and A raised to 5, simply you are going to multiply the matrices. For A square, you are going to multiply A raised to 1 multiplied by A raised to 1. Now, you know how the matrix multiplication is done. Okay, so the first row of the first matrix and the first column of the first matrix, each elements 1 by 1 are multiplied, like 0 into 0. Then they are summed up, plus 1 into 0, plus 1 into 0, plus 0 into 1. So, it will become what? It will become 0. So likewise other entries are done. So you get an A square matrix. Now for the A cube matrix, what you will do? You will multiply the A square matrix with A raised to power 1 matrix. Okay. So you will get the resultant A cube matrix. For A raised to power 4, you will multiply the A cube matrix with A raised to power 1 matrix. You will get the resultant A raised to power 4 matrix. So this is how you calculate the path matrix. So now based on the above calculation, we define matrix B as B raised to R is equals to A raised to 1 plus A raised to 2 plus A raised to 3 up to A raised to R. An entry in the ith row and jth column of matrix BR gives the number of path of length R or less than R from vertex Vi to Vj. So the main goal to define the matrix B is to obtain the path matrix P. So the path matrix P can be calculated from B by setting an entry P of ij is equals to 1 if B of ij is non-zero and P of ij is 0 if otherwise. So the path matrix is used to show whether there exists a simple path from node Vi to Vj. So in this previous example, we have seen A raised to 4 has some values which are other than zeros and 1. Similarly, A raised to 3 has some values which are other than zeros and 1. Similarly for a square. Okay. So what we will do, we will create a matrix B. So matrix B will create in such a way that we will write 1 if there exists a positive value or there exists a simple edge between P of ij. Let it be a direct path or let it be an indirect path. If there exists a path between Vi to Vj, then it will have the value as 1, otherwise 0. So let us now sum up all the matrices. A1, this is A1, this is A2, A square, A cube and A raised to 4. So we will get a B matrix here. Now for every non-negative value we are putting 1 here in the corresponding path matrix. So if you can see, there are all non-zero value. So all are the non-zeros. So all the values in the path matrix will be 1. What does this conclude? This concludes that we can reach from any node to every other node. Means there is a path existing between the any two nodes in the given graph. Let it be a path of length 1 or 2 or 3 or 4. Okay, so let it be a direct path or an indirect path, but there exists a path between the two edges in any of the vertices, in the graph. Okay, so this is how the path matrix is calculated from the adjacency matrix. I hope you all have understood this. So thank you for patiently listening. Our next topic is representation of graph using adjacency list.